start recording. I finally remembered to remove the last several weeks of recording from my hard drive, so the laptop will hopefully won't crash this time. Let's see, in terms of announcements, your last assignment is up. Other than that, it's just that and a final exam and the mini quizzes that we keep forgetting to write, and you're out of here. So almost done. And I think that's basically it for announcements. I guess Chris just released your homework grades for homework 2. And he doesn't know it yet, but homework 3 grades are forthcoming soon. Yeah. Any questions, comments, concerns as we approach the final days of this course? I keep saying that. It's kind of wishful thinking. I guess there's still like 3 weeks plus a final, but we're getting there. Not that I don't love all of you very much. Okay. Fantastic. So since you're all quiet as always, we'll get started with the technical content for the day. So if you recall, this last part of this course, 6S955, is we had a bit of a reset, right? We spent a lot of weeks going really deep into different optimization techniques, and now you guys are all ninjas at all the cool different optimization algorithms out there, from extremely specialized to extremely broad. And now we're looking at different problems where the unknown is a function, or in this case, a derived quantity about a function, rather than the unknown being like a point, like the optimum of an objective function. Right? And in particular, in our previous lecture, we talked about interpolation, which is just the simple problem of filling information between data points. The good news is that I think these couple lectures are maybe a little easier than what's come before them. Like this is a little closer to high school calculus. Today, we're going to continue that story, and rather than just talking about interpolation, now we're going to talk about integration. So I think my plan is, I noticed when I was going through my notes this morning that there was too much for all this to get squeezed into a day. But we'll try to do integration today and maybe differentiation on Thursday. Seems like a reasonable split. And maybe we'll even do a little bit more autodiff than is covered in the textbooks and slides, since that seems to be the tool we all care about these days. Right, so to put it very simply, our previous lecture, our job was to find f of x given, samples of a function, or access to evaluating that function depending on precisely the setting that we're in. Today, we're trying to compute some derived quantities, like the derivative or the integral of these things. There's no shortage of applications where this stuff comes up. I think you can all name applications of integrals in your everyday life. But specifically, numerical integration comes up quite a bit in different application areas. And we'll highlight a few of them now, and then we'll dive into some of the methods. Of course, for some functions out there that we just want to evaluate, they actually are just defined in terms of integrals. So I think the most famous one of these is called ERF. Anybody remember what ERF stands for? Error function. Yeah. It's the cumulative distribution function of a unit Gaussian distribution. This is a function that shows up in all kinds of signal processing and image processing techniques. It shows up in statistics. It shows up in machine learning. The only problem is that this is a well-defined function of x, right? And it's perfectly smooth. I guess the plot of this thing looks roughly like. Well, actually, I forget. So ERF, I guess it's integrated from 0. So it looks like, looks like a sigmoid. In fact, my bet is someone out there in the universe has used this thing as a neural network activation, because why not?
What they do in economics, they call it probit regression rather than logic, which is statistical regression.
Neat. Okay, so apparently if you replace an exponential with this thing, you get some weird type of regression I've never heard of. Cool. But in any event, the problem here is that if I even want to evaluate ERF at a point x, I need to compute this integral. This is actually a particularly annoying integral to do. Although the integrand here is relatively smooth. But there's any number of other places where you want to do it. I think a nice, very concrete example of an algorithm that I think is really cute. We don't do much probability in this class. If we had another 3 weeks, we would do a lot of probability, because that's sort of the big missing piece of numerical methods that we don't get to here. But I kind of leave it out here because I feel like you're more likely to see that in other classes in this department. Here's a good one. Let's say that I have a probability density function, p of x, on the unit interval. So what do I mean by that? By the way, the strategy works for domains that aren't the unit interval, but makes calculus mildly more annoying. So here's 0, here's 1, and let's say that I define some function that's positive and integrates to 1, and I want to sample from this thing, right? So I want to throw darts, and they're more likely to end up in the middle than on this side. Very, very typical task. Now, it would be really annoying if a piece of numerical software, every time we wanted to sample from a new p of x, we had to come up with a completely different algorithm. And lucky for us, we don't, because there's a nice strategy out here, which is called inverse transform sampling, by the way, in case you're curious. Unfortunately, this is like hashtag spoiler alert, basically what's going on in this algorithm. And the basic point here is that, like, if you look in the code in C++, MATLAB, Python, Fortran, whatever your numerical method of choice, COBOL, what are Eiffel? What are some of the old ones? Formula One? I don't know. Right, and let's say that basically the only thing I know how to do here is not to sample from some fancy, like, p of x here, but rather the only thing I know how to do is to draw a big X from the uniform distribution on 0, 1. Okay, all I can do is just randomly throw darts at the unit interval. And many of you have probably even implemented code that does precisely this, using your favorite pseudo-random generator. You know? I would love to cover algorithms for that, but that's like way out of the scope of this class. What's the usual trick? You like randomly draw an integer and then divide by int max, and then that turns out to be slightly biased because those two things might be, anyway. Where was I? Yeah, okay, so the only thing I know how to do is throw darts uniformly in between the unit interval. I'd like to bias my sampler by putting a weighting p of x. What am I to do? Anybody know the strategy here? The name kind of gives it away. The TA does, which is good. He's read the book, clearly. Yes, Axel? Almost. Does P have an inverse? Like, for example, like here you can see it has two places where it takes the same value. Well, conveniently for us, I like the little sly pointing that Chris is doing right now. If you look on the slide, you'll see that we have defined a slightly different function, which I have, for some puzzling reason, called f of t, which is a function that inputs a little t and gives me the integral from 0 to t of p of, I guess, x dx. Anybody know what this is usually called in statistics or probability? Yeah, this is the cumulative distribution function, right? It's like the amount of stuff to the left of a point x, right? So here's going to be our basic algorithm here, is we're going to draw uniformly a point x, and then we are just going to take our sample y to be equal to big F inverse of x. First of all, notice that like big F has an inverse because this is an increasing function, right? P is positive. And maybe we'll assume that it's strictly positive to avoid. Otherwise, you have to be a little careful what you mean by inverse. Okay. Let's check this little fact just for fun. We've got a minute. Right. So here's one way to do it. So in particular, one way to understand the CDF here, if you think about it, is that it's like the likelihood that x is less than t, right? Because it's kind of the sum of all the probabilities less than t. Okay. So in particular, let's look at the following value, which is the probability that y, right, our computed value here, is less than or equal to some value z. Right? And of course, this is the probability that, just by definition, big F inverse of x is less than or equal to z, like that. This is the most complicated probability calculation we'll do in this class. Maybe, I mean, we could like prove convergence of stochastic integration, but yeah. Okay, so f is increasing, so this is a lucky circumstance where this is actually exactly the same as x being less than or equal to f of z. You guys see that? Like this only works because f is monotonic. Right? Okay. So, what is this thing? Well, this is exactly our CDF function, right? So, what did we show? Well, in essence, we just showed that big F is the CDF of a random variable y, right? That's like precisely what we've shown in this chain of equalities. So, in other words, y is drawn from the distribution P. So anyway, this is a very simple little derivation, but what it's saying is it actually gives us a very simple algorithm involving computing integrals for sampling from an arbitrary probability distribution. Do you see that? So like, what do? I want to sample from p of x, but p of x is some weird function that I don't know much about. But I can just randomly throw uniform samples between 0 and 1. So I do that, and then I just put it through big F inverse, which is defined in terms of integration. Yeah, make sense? Notice actually, this is defined in terms of integration, but we've inverted it. So you actually have integration and a root finding problem sitting here. So it's synthesizing some of the methods we talked about before. Any questions? This is just like a little simple, fun application of numerical integration. Yes?
This is actually using practice?
Yes.
In real life?
In real life, yes,
Okay.
yeah. I think if you look at the implementations of a lot of the very simple kind of 1D samplers and your favorite numerical code, this is what they're doing. To put it differently, I challenge you to come up with a different algorithm for sampling from your favorite.
Gaussians, at least, they have more specialized ones.
This
Muller, or whatever it's called.
could be. No, Muller is he's the FBI guy, actually. But there's no, I mean, like, there are all kinds of distributions out there in the universe. I don't think that people, I mean, I'm sure there's like random mathematicians out there that build their whole career on like sampling from some random thing. But no, for sampling from a generic P, I think this is usually a strategy people use. You can actually modify it ever so slightly where if X is distributed with something else whose density you know, then you like look at the ratio or something here, but I forget exactly what it is. Cool. So anyway, this is one nice little trick. Again, this is called inverse transform sampling. It's just a tidy little application of numerical integration. But there's no shortage of one. So like the students in this class, I think, are roughly divided among like the vision graphics students and the kind of machine learning folks, and then random math guy. And of course, in computer graphics, numerical integration arguably is the role of all 3D graphics software, even if you don't think about it all that much. So you can understand tools that render a 3D scene as computing a very coarse approximation to the solution of an integral equation. And in fact, there are some really fancy rendering algorithms out there that actually try to discretize these integrals and just solve the system, which is just wild. What's even more wild is that this dates back to like the 70s and 80s. Like it's way before they had the computing power to do this kind of thing. And it looks a little bit something like this. So it's a fun application. And it actually, I think numerical analysts kind of view graphics as its own little discipline that has no, you know, like maybe Monte Carlo is the relevant piece, but actually like numerical integration, even the sort of classical stuff is relevant here. So here's how you derive such a thing. So let's define a function I of x comma y to be the intensity of the amount of light that is transferring from y to x, right? So like if I is big, then like a point y, like this light bulb, is transmitting lots of light to my forehead. Okay, so for every pair of points in a 3D scene, I have this function I. So now, here's kind of an interesting thing that I can do. We can write a really giant equation, and we can view almost all rendering tools as really bad approximations of this thing. And it's kind of fun to actually look back. This goes back to, I think Kajia is a famous author, K-A-J. I think it's an A. I'm not 100% confident. Very famous guy. Okay, and it looks something like this. This is going to be a geometry term. G stands for geometry here. We have an emission term plus a surface integral of rho x, y, z. This is just going to be reflectance and scatter times I of y, z, d, z. Okay, so what does this equation say? So here, we're going to account for occlusion. So for example, let's say that I have a light source, and I have Chris's face. He's smiling. See, it's just like that. You know, and now I have a big cloud of smoke in between. Right? It's a very he's giving the rock show that he does after his job as UTA. Then essentially I have a term which is going to downweight the amount of light that goes from y to x. Okay? We have this thing, which is the emission term. So this is like the amount of light that's actually at our light bulb. Right? So some objects in your scene actually emit light or like convert it from some other type of energy. And now light does two things. Like for one, it just follows along paths from one point to another. This is obviously still an approximation, right? Like for example, light can do curved paths through certain materials, but we're not gonna worry about that. But it can do another thing, which is that I have a light bulb, I have a wall, the light hits the wall, and then illuminates some point on the floor, right? This is a tech. By the way, this formula shows up a lot in a particular corner of computer graphics called global illumination. Has anybody ever coded an algorithm for global illumination? Like, what are the favorite ones? Irradiance, caching. What are some of the other ones? The one like the Monte Carlo ray tracing of different sorts. Yeah. So the basic point of global illumination is like if I shine a really bright light on the wall, the floor will light up a little bit, right? That's like light bounces off of all kinds of stuff, right? And moreover, that little tiny amount of light that bounces off the floor will like illuminate something else in the room. Most rendering algorithms do not account for that, right? For example, if you think of ray tracing, right? You've got your viewer, you've got some shape, you've got your light source. It actually traces a ray from your eyeball to the very first thing that it runs into, because that's what's going to be visible to your eye, right? And then it does some lighting calculation. But the problem with this kind of model is that if there's like some light diffuser over here, it can't account for that because it needs some path all the way back to the light source from your eye. If you think about it, that's a very indirect object. Yeah? If you want an even worse case, you like put you make this thing into a magnifying glass. And you'd have to kind of solve a nonlinear problem to kind of trace forward and backward in the scene. So in any event, in this situation here, this row term here is scattering. So the way to think about it, in this picture on the left-hand side, is that we have light that lands at a point X, emits from a light at point Y, and scatters through a point Z on a surface, right? So this weight rho here has to do with the material of the surface at point Z. Does that make sense? And then finally, I here is the amount of light that went from Y to Z, right? So it's saying that like, well, if I know this illumination, then I can get that illumination that bounced off of it, right? Now, when we think of computer graphics tools like video games, we think of them as algorithms, like you're given all the objects in the scene and now we produce a visualization of them all. But can anybody, so at the end of the day, the thing that we're going to draw on the computer screen is some function of I, right? What's the problem here? There's an I on both sides. So like when we think of rendering algorithms, we usually think of them as somehow like loop over all the objects in the scene and shade them. This is actually a system of equations. Like in order to get the world's best lighting, you cannot do that. And that makes perfect sense because like when I look at an object, I am seeing the integral of all the light coming into it, and that includes light bouncing off of my eyeball. Right? So there's like, this somehow circular relationship I have to do. And so if you look at rendering algorithms, what they do is one of two things. Really aggressive ones, like early video games in the 80s, just zeroed this term out, right? Like essentially what you were looking at was just light coming from a point. Other times, for example, you would sort of take this thing and you would substitute in this expression for I a second time. Do you see that? So in other words, like light bounces off of Chris's forehead onto the floor, and then from the floor onto my face. And so one way that I could account for that is to then plug in this equality a second time here, and kind of just recursively chain through this thing. But luckily for me, this row factor here is relatively small. And so after a few steps of that, I just zero it out, and I just leave the emission term. Yeah? And so you can understand a lot of graphics algorithms out there through the lens of numerical integration. These are just different ways of approximating this integral. In fact, if you like this kind of stuff, like it's a really cool perspective, and I don't think you see it in undergrad graphics. Like I think it's an advanced thing that comes later. The Google search term here is sometimes called radiosity. And this, it's like kind of amazing. I know some of you guys have taken some classes in like mechanical engineering. You may have encountered the finite element method, which is usually a technique for like solving differential equations, like, I don't know, Laplace equation. And these guys actually use finite element to solve like these really nasty rendering equations. And then what they get are these scenes where like I turn on a light and the lighting looks very soft because it's bouncing every which way before getting to your eyeball. Whereas like a typical bad rendered video game scene looks very hard. There's like very sharp edges. So anyway, if you're curious, numerical integration shows up in that world all the freaking time. There's all kinds of cool Monte Carlo estimators for integrals that show up in that world, which are essentially doing all kinds of little surface spherical integrals to like account for light coming in and bouncing out. It's a fun world. If you're looking for an excuse to do really complicated quadrature, that's a good one. Okay. Any questions about the random equation? This is a bit of a digression, but I think it's important to recognize that like, I think when you crack open your favorite numerical analysis book and you see people approximating integrals, that like, it starts to feel like high school calculus, like you're like doing Riemann integrals and dividing things into regions and but like actually these are strategies that get used, and to make really beautiful 3D stuff, like this is what's happening behind the scenes, are just souped up versions of the algorithms we'll talk about here. That's my cheerleading for the day. See, so it's applicable to probability and to graphics, and to all kinds of other things as well. So for example, if you're in image processing, of course, people do integrals all the time to do things like blur out an image. So here, gee, it's like a Gaussian filter, and I want to take this photo of a fish and make it blurry. I can do that by running it through this convolution, which is nothing more than an integral. Those of you who like Fourier transforms, of course, that's a very different type of integral, but one nonetheless. So anyway, I'm not going to waste a whole lot of time. You know, I don't think I need to convince a room full of MIT graduate students that like computing integrals is an important thing. But numerically computing integrals is a thing that so many of these tools do, or by the way, they avoid it like the devil. And it's going to turn out that numerical integration is not going to be so hard in like 1D or maybe 2D. And then dimension basically like 5-ish or bigger, it gets really, really tough to do this thing accurately. Can anybody think of any examples where this happens? Chris can, because he just published a paper on it. So, for example, what's all the rage these days in fancy generative AI stuff are these diffusion samplers. And one thing you might notice is that they're built off of a particular object called the score function. Anybody, do you guys know this math at all, or like cracked open a popular science AI book to kind of understand? So the basic idea is that in a lot of areas of statistics, you don't work with the probability distribution. You work with the gradient of the log of the probability distribution. And you know, there's some, you know, you can try to like get very philosophical about it, but I think the reality is for a lot of people it's just a mathematical convenience. And there's a reason, which is that oftentimes the annoying part of probability shows up in the denominator. And so there's a lot of expressions in probability where you get like, you know, the likelihood of some event, you know, divided by, you know, the sum of likelihoods of a bunch of other events. And it's this thing that turns into some giant integral over your whole state space, that somehow these methods that are making use of like the log of this object don't have to touch because it ends up in some other term in their sum, right? So as probably the most famous example of that, if we take a look at Bayes' rule, you know, so the likelihood of some event x given y, we can flip that backward to get the likelihood, or we can flip that backward to write it in terms of the likelihood of event y in terms of x. Oftentimes we want to like find the maximum likely estimate of the left-hand side. And the way I'm going to do that is by gradient descent on some expression that looks like the right-hand side. And the problem is that this integral down here is typically gigantic, because x is like the state of every possible thing in my entire system that I'm trying to deal with, right? And so the good news is if you work in the log of this thing, oftentimes this becomes a constant, and the gradient just involves like the first term, or you just ignore it. So in any event, I would say actually the main place where you see all kinds of wild and crazy quadrature methods show up a lot, basically just normalizing probability distribution to integrate to 1. Like, that turns out to be a really challenging thing to do in practice. Right, so these are really hard quadrature problems. Today we're not going to get too close to like super state-of-the-art methods for this, but we'll at least talk about some of the basic strategies and like why this problem might be well or ill conditioned, which I think is a good starting point. And one that, by the way, I think oftentimes gets omitted. Like when you take problems in, like I'm trying to think of a good research area, like probabilistic inference, and then even more so in reinforcement learning specifically. Like they do quadrature on integrals that they have no business integrating, like high dimensional things that like really, anyway, from perspective of numerical analysis, like the numbers you're getting are garbage, but somehow these things work okay anyway. It's just magic. Okay. for us today, as always, I think in this class we always seem to follow the same pattern. We're going to do the one-dimensional problem first, and then we're going to talk about how to do it in more than one dimension. So to start, we're going to talk about, given a sampling of n values of a function, f of x1 to f of xn, our job is to approximate the integral of f from a to b. So there's a lot of different versions of this story that I think depend a little bit specifically on the setting that we're in. So for example, maybe f I've measured like in a data collection procedure. You know, I've collected people's survey results, and somehow this is an approximation of an f. In that case, I don't get to change the x's, and I don't get to query f anymore, right? Like that's the data I have. Somebody hands me the x's, and I want to do the best that I can. There's a different version of this problem where I get to strategically choose x's and then evaluate f. You see that those are slightly different? Like sometimes the f of x's are just a list that somebody hands me, and sometimes they say, oh, I have a black box and it evaluate f at any given x, and my goal is to like get a good approximation of the integral without using too many samples. Right? These are slightly different things. Yeah, so even in 1D, these two problems are different. And you can imagine how they're different. Like, for instance, I might want to do this adaptively. Like maybe I can query f, like somebody gives me a black box piece of code that inputs x and outputs f of x. Then it might make sense for me to like sample kind of coarsely, figure out where the interesting action is, and then resample a little more. Whereas, you know, in other settings, I just can't do that. Okay. So this problem is typically called quadrature. I think quadrature is one of these math terms that's overloaded many different ways, but in this class, this is the term, this is what we're going to use to refer to it. This is the definition of that term in this class. This is a better sentence. And now let's talk about all kinds of fun strategies for quadrature. Even in one dimension, they're super cool. There's actually, like, this is one of these areas that every year when I teach this stuff, it's been a while, but every time I do, I think like, ugh, this is going to be boring because like integral formulas are boring. And then you actually learn there's some really clever little tricks. And they go back again to like shortly after the invention of calculus. Like people really wanted to do this stuff by hand. And so you see a lot of the early classical mathematicians attached to this stuff. Okay, so our first strategy is going to be basically an extension of our previous lecture. This is a very simple one. And this is a strategy called interpolatory quadrature, exactly what it sounds like. So our previous lecture basically told us what? It told us if I have samples of a function, it gives us a strategy for how to fill in values of the function in between, right? And that immediately suggests a strategy for quadrature, right? So I basically interpolate the values, and now I have an actual function that I can integrate. I think this is a totally straightforward strategy. And the good news is that integrals are linear, right? If I add two functions and then I integrate them, that's the same thing as integrating the two functions and then adding the result, right? And so that allows us to do calculations like what's on the screen here. So let's say that I write f in a basis. Remember that was our strategy from the previous lecture. Then essentially I can pass the integral under the sum, right? And notice that like the phi i's are basis functions. For example, last time we used like different polynomials. Hopefully you remembered that story. So I can just pre-compute that. And now basically what I have is a weighted sum of the a's. Does this expression make sense? But the thing to remember is like who depends on what. Right, so here the c's only depend on the basis functions, right? So for example, 1, x squared, whereas the ai's here depend on the actual function you're interpolating. Question?
So last time when we were doing polynomials, why can't you just integrate those like analytically?
We totally can, and let's do exactly that example, Axel, which is may or may not be exactly what's next in my notes here. So let's do an example. This is going to basically motivate for us a funny looking formula that I think you can understand almost all integration rules in terms of. Almost all. So in particular, as our colleague suggests here, let's say that I write f of x as the sum over k of a k x to the k. Right? And now, I will give you a formula because I'm that nice. What is the integral from 0 to 1 of x to the k? Thanks, Harry. 1 over k plus 1. I guess I didn't give you the formula. But this guy, he can do it in his head. Cool? So in particular, what is the integral from 0 to 1 of f of x dx? Well, this is nothing more than the sum over k, ak, integral 0, 1, x to the k. dx, right? Notice that this thing now does not depend on our interpolation task, right? Our interpolation task is kind of encoded in the a's, yeah? And so in particular, you get kind of an interesting quadrature rule, which is that this is a to the k over k plus what? Ak rather, not a to the k. That makes sense? I think the reason to write this is that like this expression, if I left this line out, it's like not obvious this has anything to do with integrating a function. But the reality is that like once I've written it in this basis, then like there's just some linear combination of the basis weights that's leading me to the integral formula. Which is perfect sense. I mean, this is just a consequence of linearity. Yes?
This is when we're using a monomial basis?
Yeah, exactly. This is monomial basis. Of course, if I use like cubic Hermite whatever basis, then I have to be a little careful with these integrals here. Yeah. This strategy makes sense? You look puzzled.
You have to get the AKs.
You do have to get the AKs.
Is the least squares problem easier than like?
No, this is you still like the previous lecture still applies. To use interpolatory quadrature, I have to do this in 2 steps, right? The first thing I have to do is solve a particular linear system of equations to get the AKs. Remember what that linear system is called for this particular basis? Van something, that's right. And then I scale those things and I add them together. Yeah. Van something. You're so close. Vandermonde, thank you. Not van der Waals, that was some physics thing. Okay. Or chemistry or whatever, I don't know. Wet stuff. Okay, so this is a very simple strategy for quadrature. And it's one of many. I think here's another one, which is even kind of simpler to eyeball. So we have this Riemann integral formula, which is, I think, the typical definition of integral in your undergrad calculus class, your graduate one. Then they like kind of take the rectangles and flip them sideways. And so in this picture here, I mean, immediately this suggests a strategy for quadrature, right? Where I essentially just put little rectangles, you know, our usual Riemann integral picture that I think we've all drawn a million times, right? As I sample my function at these points, and then I stick like a little rectangle at each point. Right, and I sum up the areas of the rectangles, and that gives me some approximation of the integral. Yeah? So both of these expressions kind of lead us to an interesting form for what I can call a quadrature rule, which is a way to take f at a set of points and convert it into integral. Notice that this does not necessarily agree with the previous one. Right? Like there's no reason why Riemann integration should work well for like x to the 5th. It's rectangles. That's not rectangle. Okay. And that's, we typically write it like this, which is essentially, we can think of our quadrature rule as linearly combining values of f at different points. Right? Just some weighted average. Right? So for the Riemann sum case, the weights are just the width of the rectangles. Yeah. For the monomial basis, it's a little bit trickier, right? But like essentially, you can think of the a's as some linear function of the values of the f's. So if you kind of compose them all together, you'll still get something of this form. Do I want to write that down? No, I don't want to write that down. Okay, so it's like generically speaking, this is what we can call a quadrature rule. And I think you can understand almost all the one-dimensional integration strategies. It's basically just different choices of w's and x's. This is a subtle point. This is not a linear problem if I am allowed to choose the places where I sample my function. We're going to see that in a minute. Does this like generic form make sense? Yeah. It is linear in the f's, right? In other words, if I think of the f's as a constant, then it's linear because it's just a sum of, it's a weighted sum.
Yeah, but why do you sort of force it to be that way?
I don't. There will be different quadrature rules, and some of them, like there's sort of two different versions of this game, right? One of them is like, I know the x's a priori, and I'm given the f of x's, and my only choice in that case are the w's, right? How do I combine values of my function at different places to get an integral? There's a different version of this which says, I give you a piece of code for evaluating f, I can put it in wherever I want, and in that case, I get to choose the x's and the w's, right? There are more degrees of freedom. I think the dumb strategy that we would all do first is to just uniformly sample them, but there's of course cleverer things that we can do. Yeah, we're going to see 2 examples of that. 2 coming up soon, if I remember. Good question. Okay, so there are all kinds of quadrature rules, and because the classical mathematicians worked on them, they all named them after themselves. So like we've got a bunch of like really dumb quadrature rules that all have people's names attached to them. I suppose I should take this as like a hint for my own career rather than like, you know, naming things based on what they do. But here's a few examples. I think the most common, well-known quadrature rules are ones called Newton-Cotes quadrature rules, which you might not know the name, but you have certainly encountered these formulas before in your everyday life. These things actually kind of divide into two different categories. They're called closed and open quadrature rules. I don't know if you've ever encountered these things. The basic idea here is that I'm going to query my function f of x at like n points, right? And in the Newton-Cotes quadrature rules, I am choosing to put those points in even spacing. I don't have to, but I'm choosing to in these quadrature rules. Okay? So in this particular case, there are kind of two different ways to evenly distribute n points. You could either make like n intervals and put a point at the center of each interval, or I could put one point at the very beginning and the end of the interval, and then evenly distribute everything in between. And so essentially, the two sets of quadrature rules divide into these two categories: closed and open. Does that make sense? So like these are all the kind of things that like are not going to matter a ton if you have a bunch of x's, but matter a lot when you don't have very many x's, right? Okay. Anybody think of a Newton-Cotes quadrature rule? There are many. I'm sure you've encountered this in undergrad calculus. At least the last time I checked the high school AP calculus curriculum, it was there. Well, here's a very simple one. This is the midpoint rule. This is Newton-Cotes. This is an open integrator, right? Because I have a single interval with one data point right at the center of it, and I approximate it with the area of a rectangle, right? Can anybody think of an example of a closed quadrature rule with two values of f instead of one? Chris can. Two endpoints is a closed thing. What do I do with the two values? I could. The trapezoid rule. Thank you, Axel. These are not, yeah, for once, I'm not asking complicated stuff. We're not deriving fancy BFGS formula. We're back in like simple calculus land. There are many other ones. I think another one that is like a favorite trivia thing among high school calculus students is this thing called Simpson's rule, where you have three values and you make a parabola and then you integrate that object. That's it. The Newton-Cotes quadrature rules are really simple. I mean, they're just like essentially ways to take like very small numbers of data points, interpolate them with polynomial, and then integrate. Yep. So these quadrature rules are pretty simple, and then I think, and essentially, by the way, all I'm doing is giving names to things that I think you guys would all just do at home if I asked you to approximate an integral. Like, I don't think this is unreasonable at all. Probably you combine them together, and that would create what numerical analysts call a composite quadrature rule. Right? So like Newton-Cotes is literally like fit a polynomial to all of your data and integrate it. And then what composite rules say is that I'm going to take my data, kind of divide it into smaller pieces, and integrate each one with some other quadrature rule. So for example, here you can see midpoint rule, right? So notice that this does indeed fall into our form for a quadrature rule. So here we have this xi plus 1 plus xi over 2, right? So that's like the location where I evaluate my function. And this is the weight in front of it. It's just delta x for midpoint. Okay? This is simple stuff. Like, it's really not supposed to be complicated. To do trapezoid, as Axel suggests, you take the value on the two ends of the interval and you average them together. And that'll give you a quadrature rule like this. Notice, like, there's sort of two different ways to write the sum. One is the sort of obvious one. The second one, I've just unrolled it a bit. I think the second one is kind of useful, and we're going to come back to it in a second. Like the first one, and in fact, I'd say the picture below, like if I asked you guys to vote, so here's the midpoint rule, here's trapezoid rule, it's the same function, it's shifted up and down a little bit because I'm bad at slides in LaTeX, sorry. What do we think is probably more accurate as an integrator? What do you think? Like midpoint, trapezoid, what do we vote? Trapezoid, we got one vote for trapezoid. Harry's doing his calculations real fast. What was that? Trapezoid. We got 2 votes for trapezoid. Chris is on his laptop. Paul's asleep. Well, even if I equalize for the number of sample points, how about that? I'll give you that. So it feels like certainly this picture, this function gets a little closer. On the other hand, like if we look at this weird form on the bottom, notice it looks an awful lot like midpoint. It's basically just averaging all the values And in fact, we put this weird 1/2 weight only on the first and the last one, which feels a little fishy. Like somehow, like why should like this is not democratic. Like the first and the last guys don't get as much vote as the middle ones. So we're going to come back to that in a minute. And in fact, actually, the situation gets even weirder. So I could take the same set of n values and I could divide them into sets of 3, and then I could use Simpson's rule, and that would create something called composite Simpson rule, which maybe feels even more accurate, but it's actually not obvious if I equalize for the number of places that I evaluate my function. You see that? Like this approximation might look a little better, but notice now my quadrature rule is super strange. It's got like a 2 and a 4 on every other term. And like, why should it be that every other place I evaluate my integral gets half the weight? It's like not. So I think this is one of these cases where depending on how you write your formula, it can be suggestive of a mathematical result that we haven't proven. And then if you write it some other way, suddenly it like looks like, oh, wait, this quadrature rule maybe isn't so good, right? Like I could have taken these n values and rather than weight them with like 2s and 4s, I could put like just the same weight in front of all of them, right? So suddenly our story gets a little murky. Does that make sense? So comparing these quadrature rules is actually like a very tricky matter, and it's one you have to do quite carefully. As always, I keep trying to make this point to you guys. Like this field matters. We should do it carefully. Okay. So of course that suggests our usual question, which is we need to choose. We have many different options for our quadrature rule, and we don't know which one is best. Yep. So let's do some calculations and see if we can figure that out amongst ourselves. Here's the right notes. Is it okay if I erase our monomial quadrature rule here? Cool. And this leads to, I think, like there's a lot of things that we do in this class that I think are maybe not obvious because it's like some complicated algorithm. This is the first one that I think is like mildly surprising, which is, and it's like a fun trivia fact. Maybe you've seen it before. Essentially what we're going to show is that midpoint and trapezoid rule are actually equally accurate. And if you look at the constants involved, it's midpoint actually wins, which is a little surprising because it feels like it shouldn't be the case, right? So let's actually do that. Oh no, I gave it away, I'm sorry. So in particular, here's going to be our setup. So we've got an interval a and b, and we've got c is 1/2 a plus b. Okay? And what we're going to do to prove all of these different bounds is we're going to take the Taylor series about c, right? So I've got my complicated function, whatever it is, and now I'm going to take c and I'm going to approximate it with like a parabola or something like that. Okay? So when I do that, I get the following function, f of x equal to f of c. Luckily for us, this is a one-dimensional thing, so we don't have to do all these fancy Jacobians. Well, that'd be a good, boring homework problem. We've got plus f prime of c, x minus c. How many terms do we want to do in this Taylor series? We're actually going to need quite a few, sadly. Plus 1/2 f double prime of c, x minus c, plus 1/6 f triple prime of c, x minus c. Maybe one more just for fun. What is it? 24, I guess. F fourth derivative of c. Oops, there's a square and a cubed, and x minus c to the fourth. Okay, have I managed to Taylor series correctly? It's important to do this at least once before breakfast. I'm very hungry. Okay, so right, so it's important not to think when you write proofs like this, and the reason that I think Taylor seriesization about c is kind of nice is that it's symmetric. In particular, what's going to happen when I integrate f from a to b? Just to give like a little like preview. So in particular, let's look at this term here. This is linear term. Well, so the only thing that depends on x is the linear part here, right? So this is the average value of x minus c, where c is in between a and b. So what's going to be the integral of this thing? 0. That's right. And in fact, every odd term in this sequence goes away. This is like a nice mathematical convenience. Do you guys see that? Is everybody following, tracking? Okay. So in particular, we have the integral from a to b of f of x dx is going to be equal to, well, what's the integral of a to b of f of c? Well, it's just a constant, right? So it's just b minus a f of c, like that. The integral of this guy is 0. The integral of this guy, luckily for you, your instructor was kind enough to put it into Wolfram alpha and then realize that it's actually a really dumb integral I could have done by hand. But in particular, this is 1 over 24 times f double prime of c b minus a cubed. You can trust me or you can do it by hand really quick. Okay, and then just for fun, we'll do, so now what is the integral of this guy from a to b? 0. Great, that one I can do. What's the integral of this guy from a to b? Any guesses? You shouldn't, it's a weird one. So you have 1 over 1,920 times the fourth derivative at c times b minus a to the fifth plus stuff. So notice we're cooking with gas. We've just killed every other term in our Taylor series. Like life is pretty good. Whew. So now what? Well, this is actually one of these the proofs that I think is like you look at it for a second and like you realize that like something happened that we kind of forgot about. What is this? What is b minus a times f of c? It's a quadrature rule. This is the midpoint rule. Do you see that? So just by integrating the Taylor series, like the midpoint rule just accidentally fell out. I mean, not accidentally at all. It's because like this is a very sensible way to compute an integral, right? So this is the midpoint rule. And in fact, I can just rearrange this expression. I mean, I can move this guy over here and that guy over there, right? And now what am I going to get? Well, I'll get b minus a times f of c, which is, again, our midpoint rule. Well, if I subtract everything else here, then I get that this is the integral from a to b of f of x dx minus 1 over 24 f double prime of c b minus a cubed plus maybe big O of big A, b minus a to the fifth. Okay? So all I did was rearrange this expression here. But notice, like, what is this thing saying? This is saying that these guys are equal to each other. So in other words, the midpoint rule agrees with the integral up to an error term, and the dominant part of the error term is cubic. Right? So this is like big O of delta x cubed. What's that? It's pretty good, but notice that this is for a single interval. I mean, usually we talk about composite rules. We haven't done that yet. So like delta x is probably pretty small. But now, okay, so that's midpoint. And I think the key observation here and the reason that like this magic formula is happening is symmetry. That like essentially because every other term here is 0 is why midpoint and trapezoid kind of end up with the same value. Okay? So now let's do trapezoid. So first of all, let's, I don't know, let's put a big star on that because we're excited about it. Okay, so now let's go back to this expression for f of x. Cool. And here's what I'm going to do. I'm going to write an expression for f of a and f of b by plugging in x equals a and x equals b. So in other words, I've taken a Taylor series about the midpoint, and now I'm going to evaluate what the value is at the ends of the interval. Okay? So in particular, what is f of a? Well, it's f of c plus f prime of c, a minus c plus 1/2 f double prime of c, a minus c squared plus 1/6 f triple prime of c, a minus c cubed, and I believe that's good enough. Yep. Luckily for you, like when I wrote this proof the first time, I did way more terms than were needed because I wasn't really sure, and then I went back and removed some. Okay. So you guys see that like in particular, starting with this expression, I can plug in x equals a. I can also do that for b. So I'm going to get f of b is equal to f of c plus f prime of c, b minus c plus 1/2 f double prime of c, b minus c plus 1 squared plus 1/6 f triple prime of c, b minus c plus, okay. Getting quick at this thing. The trick is giving up on legibility. Okay, and the reason that I want to do that, this is so sneaky. I love this. I love these tricks. I love these little calculus things. They're so much fun. Notice that I can assemble the trapezoid rule out of these two values, right? Because the trapezoid rule is b minus a times the average of these two things. Sneaky, huh? Now I have some expression on the right-hand side. So, okay. So what's the trapezoid rule? Is equal to b minus a times f of b plus f of a over 2, like that. Make sense? So what I'm going to do, which is mildly annoying, admittedly, is take these two things and plug them in for f of a and f of b. And the reason for doing that is that I'm trying to, like, what is my end goal? It's really to compare to this Taylor expansion, right? That's what I'm after. Okay. So, what do I get? Well, the first term that I'm going to get, I'll get b minus a times the average of f of c and f of c, right? So it's just, everybody agree that's the first term in my sum here? Okay. Well, what's the next one going to be? Well, this is mildly annoying. Okay, so I'm going to have a 1/2, and I'm going to combine that with the other 1/2 here. So I've got a 1/4 b minus a, right? That's this b minus a factor, and then times the sum of these two guys. So it's f double prime of c, and we've got an a minus c squared plus b minus c squared, like that. That make sense? I think this stuff is mildly ugly, but such is life. Okay. And luckily for us, your instructor did a lot of boring arithmetic that I'm going to allow you guys to skip for once. That this thing is the same as b minus a f of c plus, and if you just kind of expand these squares and then cancel out terms, what you're going to end up with is 1/8 f double prime of c times b minus a cubed. Okay? By the way, in order to do that, you're going to need to plug in here the fact that c is equal to a plus b over 2, which is like a mildly ugly calculation, which is why we're just going to skip it, if that's okay. Are there any questions? I can certainly do it, but don't make me do that, please. Okay. Cool. So, why did I do that? So, what is the first term? What is this thing? It's a midpoint rule, again, right? Yeah, midpoint. So, first we can derive the coarse result, and then maybe we'll derive the finer result. So, what is the coarse result? Well, we know the midpoint is equal to the integral plus a cubic term. We know that trapezoid is midpoint plus a cubic term. So overall, this whole thing is going to be midpoint plus big O of delta x cubed. So in fact, the accuracy of these two things is exactly the same from a big O perspective. Yeah? So you might ask then, like, well, which one of these should we choose? Like, maybe it could be still, like the trapezoid one still feels more accurate. Like, it's like still touching the function more closely. Like, maybe that's reflected in these constants here. You have to be the tiniest bit careful. I have a 1/8 here. I've got a 1/24 there. But notice that this 1/8 is relating trapezoid and midpoint. It's not relating trapezoid and integral. You have to be the tiniest bit careful. But what do we know? Well, we know that this is equal to the integral plus this term here. This is not in my notes, so we'll see if we manage to get it right. Okay, so this, we know that midpoint is equal to the integral from a to b of f of x dx minus 1 over 24 f double prime of c b minus a cubed plus big O of delta x to the fifth, right? And then plus, we can't forget this term we had before, right? So this is plus 1/8 f double prime of c b minus a cubed plus another big O of x to the fifth. So like whatever. Sorry, got distracted drawing a triangle. That makes sense what I did here. So I just took that expression there and plugged it in here. Okay, so we've got a minus 1/24 f double prime b minus a. We got a plus 1/8. What's 1/8 minus 1/24? Okay, so the 1/8 is the same thing as 3/24. 1/12, that's right. So this is equal to integral from a to b of x dx plus 1/12 f prime of c b minus a cubed plus big O delta x to the fifth. Notice it's still, the accuracy is still cubic because the thing we wanted was this guy. We're just adding one additional term. Does that make sense? So now we can do a little bit of comparison. So first of all, any questions about the arithmetic we did? Notice these are just fun, like Taylor series gymnastics. We would do this all day. It's fun, really. Okay, but take a look. So we've got a factor of 1/12 in front of our error term for trapezoid. We have a factor of 1/24 for our error term for midpoint. So what do we conclude? Midpoint is actually twice as accurate as trapezoid, which is a surprising fact. Yeah. Okay. Any questions about that little derivation? I think it's like kind of cool that this happens. Like this is just a weird circumstance of math. Okay. Now we have to be the tiniest bit careful. So oftentimes when you see people talk about midpoint and trapezoid rule, they'll say that they're quadratic accurate integrators. And that's a little weird because it looks like it's cubic. Does anybody know why we use this terminology? That's exactly right. So like typically I don't integrate from 0 to delta x. I integrate from 0 to 1, right? And so then I have to sort of add a factor. Like the question is, well, how many delta x's do I need in order to get from 0 to 1, right? And so that's it's gonna be like roughly 1 over delta x. Right? In particular, like if the spacing between, here's a way to think about it, is that like, you know, I've got, here's A, here's B, here's a bunch of spaces that are all delta x, right? The question is how many of these intervals are there? Well, it's like basically B minus A over delta x, right? So in other words, as delta x goes to 0, we're going to need more applications of this rule. So in effect, that's going to put one more factor of b minus a in front of these error terms. And that's why usually we talk about what's called the composite accuracy of these integrators, which is that like you need to like down everything by 1 power. Does that make sense?
The same thing as like local truncation error versus global truncation error.
I don't know what those terms are.
These are the buzzwords I learned in my undergrad numerical class.
Then probably. But like in general, this is going to happen again when we do numerical ODE. That like the thing that we care about is like an integral over 2 fixed endpoints, whereas this expansion, like, sure, it shows that as delta x goes to 0, this becomes more accurate at a particular rate, but it also is giving you a different integral every time you change delta x, which is a little bit unfair. Yeah. Okay. So these are the simplest strategies for quadrature. They're called Newton-Cotes integrators. They all have evenly spaced samples. I think a reasonable question, and one that I think Axel was kind of getting at before, is like, well, why do they need to be evenly spaced? Like, what's that about, right? And in fact, I think there's a lot of argument to be said that they don't have to. And so here's another example of a strategy for deriving a quadrature rule that's yet another one that's a little bit different from the ones we've done so far. Although I believe it's equivalent in some cases. Like I think, for polynomials, these things end up being the same. Is it okay if I erase our like billion Taylor series merge here? Okay. Ugh. Yeah. So here's a fun thing that I can do. Let's say I know some integrals. I know a lot of integrals. It's true. Geometry person, I also know all the angles. So here's a basic strategy people use to derive different quadrature rules is something that people call the method. I love that they give these things names. Undetermined coefficients. Okay? It's mysterious sounding when you write it like this. Okay? And here's going to be the basic trick. I want my quadrature rule, Q of f, to say is equal to the sum over k of, did I use W's? I used W's. W k f k f, oh sorry, no fk, just f, right? Of xk. And we've all decided like this is a pretty reasonable quadrature rule. In fact, it'd be like a little bit surprising if your quadrature rule didn't look like this, right? Because quadratures, like integrals are linear. Yeah. And so this is just like a different strategy of deriving a quadrature rule, and it goes a little bit something like this. So like let's say that I happen to have some function f sub I, and I just know that the integral of from a to b of f of I dx x dx is just like a value that I just have in my bag. So for example, if we go back to the previous one, like if f I here is x to the I, then we know how to integrate that in closed form. Right? Then the method of undetermined coefficients does the following. It says, aha, well, I'm going to make a quadrature rule, and I'm going to say that at the very least, my quadrature rule will work for these functions. Right? So what I can say is, for example, that the sum over k of wk of the integral from a to b of fi of x dx, right? That's, wait, what was I doing? That was dumb. I'm sorry. I'm going to erase what I just wrote because I got halfway through writing. I like wrote half of one side of an equation, half of the other, and glued them together. This is just one. So let's say that I evaluate my quadrature rule for a particular fi. Okay? So in particular, I get the sum over k wk fi of xk. Right? Now, in the method of undetermined coefficients, what I'm going to do is just say, I'm going to set this equal to the integral from a to b of fi of x dx. So in other words, like I know an integral that I know how to compute. My unknowns here are the w's, right? So I'm going to just evaluate them at the x's, and now I can do this for each of the i's, and then I'll get a linear system of equations for the w's. Does that make sense? So let's do an example. You'll see, like it's actually quite simple as an example. So here's one. The integral from a to b of x to the k dx is going to be equal to b to the k plus 1 minus a to the k plus 1 divided by k plus 1. Hopefully we all agree on this one from calculus class. Okay? This is just an integral that I know. This is not a quadrature rule. This only tells me how to integrate polynomials. Yeah? And so what I'm going to do is invent a quadrature rule that for polynomials is going to happen to give me the correct value. Might not give me the correct value for all possible functions, but it will give me the correct value for polynomials. And here's how I can do it. So let's say that I choose a bunch of points, x1 to xn, right? So and for now, we'll think of them as constants. Like maybe I evenly space them from 0 to 1, or from a to b. That make sense? Now, let's do the k equals 1 quadrature. Well, so in that case, when I evaluate here, you know, in fact, k equals 0 is even better, right? So what is fi of x to the, so let's maybe do this. Sorry. My notes and my board writing disagree on letters. Okay? And we're going to call this fi of x. Okay? So when I plug in I equals 0, my apologies for a slight change in notation here. What is the integral of x to the 0? Well, it's just b minus a, right? So that's the actual integral, which I'm going to put on one side. And the other side, I'm going to apply my quadrature rule, which says that I'm going to evaluate my function, x to the 0, at these xk's and plug it in. So this is going to be 1 w1 plus wn. So on the left hand, I'm sorry, I guess I've swapped left and right from here to here. But do you see what I've done? So on one side, I've put the actual integral. On the other side, I've put my quadrature rule. These are always approximations of each other. But in the method of undetermined coefficients, I'm just going to say, like, specifically for x to the 0, I'm going to make my quadrature rule be exact. This is a choice. This is a design decision. Yeah? So for example, like maybe I do it for x to the 1. Right? So this is going to end up being b squared minus a squared over 2 is equal to w1 x1 plus wn xn, like that. Right? And similarly, I can do this all the way up to the n minus 1 term. So I'm going to have b to the n minus a to the n over n is equal to w1 x1 to the n minus 1 plus wn xn to the n minus 1. So again, this is a choice of quadrature rules. Do you guys understand what I'm doing? I'm choosing w's so that my quadrature rule exactly integrates polynomials of up to degree n minus 1. Everybody with me so far? How do I solve this for the w's? Remember, everything here is known except the w's. It's a linear system. Thank you. We only know how to do one thing in this class. It's solve a specific equation. So let's just write this a different way. The reason that we're going to all this business, by the way, is we're eventually going to suggest this extension of the strategy, which is super cool if you're an algebraic geometer. Okay. So, in particular, what is this thing saying? It is saying that, like, we can do 1 x1 x1 to the n minus 1, 1 x2 to the n minus 1, all the way to 1 xn to the n minus 1, right? Like these are the coefficients in front of the w's, times w1 to wn is equal to, we've got like a b minus a 1/2 b squared minus a squared, all the way to a 1 over n, b to the n minus a to the n. Notice, by the way, this is the transpose of the van der Waals matrix. Can't get away from that thing in this class. Okay, so first of all, does everybody understand how this derives a quadrature rule? And do we see that for polynomials of up to degree n minus 1, this quadrature rule is exact? But notice that it's kind of doing a funny thing, right? It's saying, on the one hand, my quadrature rule is just averaging values of f at isolated points, and I'm just choosing my weighted average so that it happens to agree with the integral for a fixed set of functions that I chose. This is a weird strategy for making a quadrature rule. And there's no reason they had to be polynomials, right? I could have put anything there. Yes?
The setup here is that you have a polynomial with unknown coefficients, and you're trying to integrate it.
Not quite. I mean, like, chances are I want to integrate things that aren't polynomials, right? But it's more like I need an ansatz. I need a strategy for choosing a quadrature rule, right? Like, I would like to write an approximation of integral in this form, right? One way to do that is to say, like, I want this formula to be exact for some subset of functions. Like here I chose the polynomials of up to degree n minus 1, right? So what does that say? That says that at the very least, if I take any polynomial of up to degree n minus 1, my quadrature rule will work perfectly. There will be no error. But for any other function, I can't say anything about it. But maybe this is like kind of a reasonable way to design a quadrature rule. Yeah. And in fact, if you think about it, it actually agrees with the very first quadrature rule that we did for monomials. This is more or less exactly the same.
Isn't there sort of, yeah, I guess like that was, isn't there like some sort of way that you could sort of interpolate your polynomial? So you take your, oh, I guess you don't make a point, sorry.
Well, you do know your x's in this case. Like I've just chosen a set of x's, and this gives me a quadrature rule. And in fact, you really can convince yourself that this thing agrees with the quadrature rule that we started with for like fit of monomial function by solving the linear system of equations and then evaluate. Yeah. But here's the kind of sneaky thing. So this thing is called the method of undetermined coefficients, and so far it like looks like a pretty boring way to make a quadrature rule. I mean, like it's okay. It works, and like it works for polynomials of up to some degree. So as you can imagine, the degree of accuracy is like roughly 1 plus that degree, which is pretty good. But here's a really sneaky trick. I claim that we can come up with a strategy that will work for polynomials of up to degree 2n minus 1. Right? Like so far, this strategy, you know, like just by setting these equal signs, right? Like how many degrees of freedom are there? There's w1 to wn, right? So essentially, there's n numbers to work with here, so I can make it work for degree polynomials up to n minus 1, right? But here's a really sneaky trick. I can make the x's variables too. Do you see that? So in particular, what I'm going to say is that, yeah, my quadrature rule is of this form, but I'm going to allow in my design software to not just evenly space the x's, which feels like the right thing to do, but I'm just going to choose the x's and the w's at the same time when I design my quadrature rule, and maybe I don't make them evenly spaced. Well, now notice that like I have a lot more degrees of freedom to work with, right? I can satisfy these expressions by messing around with the x's or by messing around with the w's. And in fact, if you do your degree of freedom counting, you can double your degrees of freedom because you have w1 to wn and you have x1 to xn. Yeah? So you can actually derive undetermined coefficient quadrature rules by moving the x's around and the w's all at the same time. There's only one problem. This is a really annoying system of equations to solve. Do you see that? Because now it is no longer linear. I have powers of x, like powers of unknown variables inside of my expression. Yeah? How do you think people derive these quadrature rules in practice? Well, this is a roof finding problem. We talked about roof finding for like 3 lectures. Yeah, like this is just like a great way. So like if you want a really fancy quadrature rule, you can actually solve a numerical problem using like Broyden's method that says I have some set of closed form integrals that I know. I set all of these things equal. I have this algebraic expression on the right-hand side. These are polynomials in the unknown variables of w and x. And now I'm going to set these two things equal and just run Broyden's method to find a root. Now, in some very special cases, it turns out it's known in closed form, but typically it's not. Isn't that cool? Yes.
Oh, cool.
And this is a great way to squeeze more accuracy out of a fixed number of samples. Now, this is a super cool strategy. However, it has its drawbacks. Here's a really obvious one. Let's say that I evaluate this integral. I spend a lot of time deriving one of these quadrature rules, or I very strategically choose a set of basis functions so that this is known in closed form. I think the only one is polynomials on the unit interval. Then one thing that I could do is say, oh, wait a second, actually I wanted an integral that was 2 times more accurate. So maybe now I double my number of x's. This is a problem, which is it turns out that these x's don't nest. So like if I double n, that it is not the case that the solution to this thing with like n equals 5 and the solution where n equals 10, they're not like subsets of each other. Like you have to choose a completely different set of x's. Yeah. Which is annoying. This is a different way to put this is that these are not progressive integration rules, meaning that like for example, for Newton-Cotes, if I want to double my accuracy, I can just take every interval and divide it in half and reuse my old data. But here I cannot. That makes sense? Yeah.
What are the x values? Are they like even form?
No, they tend to like bunch up near the ends, if I recall. Yeah. So this is, I think this is a really cool problem. And by the way, yeah, if you are familiar with algebraic geometry, you know that this is like a weird giant polynomial root system. And indeed, you could spend a lot of time studying, like, does this thing have a solution? Like, what is the solution? Can I find it? You know, all that kind of stuff is all hiding here. Is it unique? Yeah. And by the way, you didn't have to do it for polynomials. You could have put anything you wanted there. Any questions about this strategy? So this is this thing has a name, which I forgot. This is a Gauss quadrature, which you optimize both the w's and the x's. Now, a different thing you might want to do is called adaptive quadrature, which is exactly what it sounds like. So maybe I'm integrating, and now I looked at my integral and I decided it wasn't accurate enough. Adaptive quadrature is a really hard problem for so many different reasons. So typically, the setting in adaptive quadrature is as follows. I have a function f of x, and essentially my goal here is to integrate f of x given just access to f. So like, I pay $1 and I get value at f of x at a given x point. Right? And so strategies for adaptive quadrature are sort of like spelunking around in like the unknown. Do you see that? So like, let's say that I have a function f, and the plot of f looks something like this. So like maybe it's like very smooth, and then it goes up, and it's smooth, and like suddenly it has something crazy like that, right? And then like an adaptive quadrature rule might say like, I need more samples of f over here than over there, right? The question is, how do I do adaptive quadrature? Like if the only thing I know is I get to put it in x and it gives me this value, how do I detect that something crazy is happening here? Any ideas? Yeah.
I guess you'd have to estimate the derivative of the function, but that's kind of numerically awful.
Yeah, one thing I do is try to estimate derivative, but like there are actually sometimes when it can be integrals of things that don't even have derivatives. It's perfectly reasonable. Any other ideas? The short answer is it's actually very hard to derive adaptive quadrature rules with guarantees. But there are a few. I think the typical thing that we do is we have all these error estimates that we derived before. One thing that I can do is do one quadrature rule and then a second quadrature rule with twice as many samples. And if those two values agree, then I sort of stop, right? And if they don't agree, then I say like, aha, like I need to keep subdividing in some region or another. And I think that's what most of the adaptive quadrature strategies end up doing. The only problem with that is if you want to use like the super highest quality integrators like these Gaussian quadrature rules, they don't nest cleanly, so I can't really do that. And so all kinds of clever engineering has gone into addressing this. So one of the most common ones is something called Quadrature. Most of the names in this lecture I think we recognize, but this one I don't think so much. Quadrature does a really, like it's so crazy, the things that these people do. Like the people are smart. So what quadrature does is says, I'm going to use a Gaussian quadrature rule. So I'm going to very carefully choose these x's. And now I'm going to double the number of x's, but the variables in this thing are only going to be the additional x's that I added. They're not going to, like I'm going to fix the first set, you know, whatever they are. And now I'm going to say like, well, I'm going to make a quadrature rule with twice as many samples, and I'm going to say, what is the best, most accurate quadrature rule I can find while leaving the previous set fixed? So I'm going to nest them inside one another. So it's like somewhere in between these Newton-Cotes quadrature and Gaussian quadrature ones. And it's useful specifically for adaptive integration because this is a good way to kind of figure out like, you know, how good is my integral estimate. Does that make sense? So in any event, maybe we'll stop there. We're right at the end of the hour. In our next lecture, we will talk about how to integrate functions of more than one variable. It's kind of funny. It takes us all this time just to do one-dimensional problems. And then we'll talk about conditioning of numerical quadrature to complete our usual suite of numerical things. And then, as you can probably guess, the next thing that we're going to do, in addition to estimating integrals, is estimate derivatives. And then we have the whole calculus toolkit at our disposal. Sound good? Fantastic. All right, folks. Well, with that, have a delightful Tuesday, and I will see you on Thursday.